Now, what replaces kinetic energy? Because I'm going to be very conventional. I'm going to say a dynamics is given me by some PQ dot term, some momentum squared like term, and some potential energy. Um, and so I know what replaces locality, what replaces kinetic energy. And so I have views that are causally related, that are to the causal future of each other, because I have causal relations. And basically, measuring the change of views from an event to an event which immediately succeeds it causally is going to define our kinetic energy. And what replaces potential energy is a comparison amongst all the pairs of views of how distinct they are or different they are. And that's using a function that we invented with Julian Barber a long time ago that can measure the complexity of a system of interactions like a graph or a city, if you will, in which what are the fundamental degrees of freedom are the views that each entity or event have of the rest of it. So that's the input in words. Where do we get, so I want to recover quantum mechanics, which means I need a probability distribution, which means I need an ensemble. And the view that I take towards the ensemble in quantum mechanics is that it's real. That is, when I say that an electron in this piece of metal right here is part of an ensemble of electrons in certain conditions, each and every one of those members of the ensemble is somewhere in the universe. So I'm going to use the function of measuring the distance between views to given one electron and its view capture throughout the universe very similar views. And that's how non-locality, of course, gets into quantum mechanics. So the quantum state represents a real ensemble of events with similar views, but spread through the universe. Since there's no space, there's nothing that permits me, that prohibits me from just doing that. So, and there's some technology associated with that. Again, I can describe if people want. So what are the claims? The claims are when I take a non-relativistic limit and you say, well, where did relativity come from? And it came from the geometry of momentum space. But I take a certain non-relativistic limit. I take ensembles where the number of similar events, which I call n, is large, and I pull out the Schrodinger equation. The Schrodinger equation depends on the probability density of the ensemble. It depends on the phase, and the phase comes from the momentum. And again, there's a lot of detail of how you pull the phase out. The potential energy is taken to be the variety of which is the sum over the distances of all acausally related pairs of the differences between them. And the kinetic energy comes from, as I was saying, the changes in the views. And that gives me the Schrodinger equation. And it also gives me controllable finite 1 over n corrections. And there is actually a lot of promise there because our friends in quantum computing laboratories can build quantum systems which have very few copies, which are not in any large ensemble, and they can play with them experimentally. So I expect that these large N corrections should be genuinely testable, and it's one of the things we've been doing is studying them. So that's the nature of the claims as far as conventional quantum mechanics is concerned. And I think let me pause here. What's coming is details of the calculations that support those claims. Let me just give you some headlines. how we describe the emergence of space-time, how we describe the emergence of matter and particles, more on this idea of variety, the idea of the real ensemble and how we compute with it, details the recovery of quantum mechanics, on and on and on. So I have a lot of details to communicate, but I think I've communicated the main ideas. And so let me go to a summary and then talk about, very briefly, about ongoing work pushing this viewpoint ahead. So to summarize, the universe consists of views of the causal past of the present events. And you should watch out for me using words like past, present, and future, because I use them like a presentist, which means that I like presence. And that's a bad joke, I'm sorry, but nobody laughed. And
We're muted though.
okay. Anyway, so that's my picture of cosmology. The universe consists of views of their causal past of present events. Systems with similar views interact. This replaces locality. That is, I didn't discuss the details, but if you're extremizing this variety, and there are two events which have very similar views of their past, they try to add members to the ensemble which are different, because you have a big negative potential energy if you start to pile up too many views which are similar. And so that's what I say there. These interact through a potential that acts to increase the diversity of views, which is called the variety. Events are causally connected by transfers of energy and momentum. Space-time is emergent from these transfers of energy and momentum. And there's a little interesting bit there, if you like Nether's theorem. There seems to be a kind of inverse or dual Nether's theorem, which is acting. I mentioned that Bohm's quantum potential comes from this variety function. And why we are not described quantum mechanically while our atoms are is because we are each wonderfully unique beings, and we don't have copies in the universe, so we're not describable as members of ensembles. So where is all this going? Well, there are, and this is almost my last slide. It's the next to the last slide. Because the work, as I've described to you, was mostly finished, and most of it was published by 2017. Since then, I've been with various people developing in different directions. The idea that the fundamental laws are irreversible and is something that needs explication, and there's work going on which develops that. Some of it with Clelia Verde. If this is really a description of nature, then general relativity, which is time reversible, should be actually an approximation to a time irreversible modified gravity theory. So there's lots of papers and conferences and so forth by cosmologists who study modified gravity theories, where they take general relativity and they tinker with it a little bit. But very few of them study whether you can modify general relativity in a way that makes it time asymmetric. And it turns out there's several consistent ways to do that. So we've been studying that with Marina, with Andre Little, with Gomez. These are all things I could talk about if people want. We're very used to the idea in thermodynamics that time irreversible systems with dissipation and friction evolve out of time reversible systems. But is there the reverse? If I fundamentally have a time irreversible system, is there a way for time reversible systems to emerge? And can we learn something about the early universe from that? Um, and I think I'm going to stop there. There are some, I have these few things to mention just to advertise work that is soon coming out. The idea of evolving laws and turns out to be very tightly integrated into quantum foundations issues. You are in quantum foundations, and I think this started with Lucy and Hardy, but may go further back, talk about generalized theories of probability and then having axioms and deriving quantum mechanics. We can approach some of these issues about a generalization of quantum mechanics, which is time asymmetric, through those methods. And there is work like that going on. And it loosely relates to an approach to evolution of laws that I call the principle of precedent. That is, systems which are similar to systems in the past appear to obey similar laws. The conventional explanation is, well, there's laws of nature and they're out there and they tell the atoms and the molecules what to do. A different proposal is that there are no such laws, there's nothing out there, but a quantum system has the ability to sample its causal past and find out when there were similar systems and similar challenges to the evolution of systems in the past, and act by precedent rather than by satisfying established unchangeable laws. And that's an idea that we're developing. And one of the things that nicely comes out of that is that you can see why, of all the different probabilistic evolution laws, unitary laws would be ones that you could get stuck in. That is, there are limit cycles and limit sets associated with the system discovering unitary dynamics. In general, and this is a paper with a number of different authors, but the lead author is Jaron Lanier, a computer scientist. We've been, and Will Cunningham, and there's 4 other people. And we've been developing a notion that we call autodidactic physics, based on analogies to machine learning. We started out wanting to debunk machine learning and ending up with a kind of understanding of the kind of dynamics that is modeled in machine learning as actually perfect for studying and modeling laws that evolve, or what we now call laws that learn. So that's some of the things that are coming out soon under these concerns, and I'll stop here. Thank you.